Time is the most personal feature of our existence. It is the thread that holds the drama of our lives together, and it is at the center of all literature, good and bad. It feeds the heart of tragedy and the pulse of adventure. Yet it remains so mysterious that some seriously question whether it even really exists. Einstein once joked that time can feel different depending on what you're doing. When you're having fun, time flies. When you're bored, it crawls. But no matter what, time is valuable. We can't get it back once it's gone. Long ago, people struggled to keep time, especially for things like travel and trade. But thanks to smart folks like John Harrison, who invented a super-accurate clock, and Einstein, who changed how we see time, we now have a universal way to keep track of time across the world. John Harrison was an English clockmaker who is best known for his invention of a highly accurate marine chronometer, a type of clock used to determine longitude at sea. In the 18th century, finding a reliable method for determining longitude while sailing across the oceans was a major challenge, as it was essential for navigation, but difficult to achieve accurately. Harrison's groundbreaking work began in the early 18th century, and over several decades, he developed a series of innovative timepieces, culminating in his most famous creation, H4, also known as the Harrison chronometer. This clock was a compact, portable timekeeping device specifically designed to maintain accurate time aboard a ship despite the motion and variations in temperature and humidity. The success of Harrison's chronometer revolutionized navigation by enabling sailors to accurately determine their longitude at sea, which significantly improved safety and efficiency in maritime travel. His work played a crucial role in solving the longitude problem and laid the foundation for modern navigation techniques. Despite facing significant challenges and encountering skepticism from established authorities, Harrison's dedication and ingenuity ultimately earned him recognition and rewards, including the Longitude Act Prize from the British government. His contributions to horology and navigation have left a lasting legacy, and he is celebrated as one of the greatest inventors in the history of maritime exploration. Einstein's big idea was that time isn't the same for everyone. It can change depending on how fast you're moving or how strong gravity is where you are. Sounds strange, right? But experiments have proven him right. For example, if you had a twin who went on a super-fast space trip while you stayed on Earth, when they came back, they'd be younger than you. It's like time behaves differently for them because of their speed. Even something as everyday as using GPS on your phone relies on Einstein's ideas. The satellites that send signals to your phone have to adjust their clocks because they're moving fast and are farther from Earth's gravity. So, time isn't as straightforward as it seems. It's like a puzzle we're still figuring out. Who knows? Maybe there are places in the universe where time works totally differently. When gravity gets incredibly strong, like near massive objects such as stars or black holes, our ability to understand it fully breaks down. John Michell, a scientist from Britain, was one of the first to think deeply about this. He suggested the idea of dark stars, which we now know as black holes. These are objects so dense and massive that not even light can escape them. Michell's idea was that if an object is big enough and dense enough, its gravity would be so strong that even light couldn't escape. He thought about how to detect these objects, suggesting that we could look for the effects they have on things around them, like how they make nearby stars move. Today, we understand black holes using a theory called general relativity, which tells us that black holes have a boundary called the event horizon. Once something crosses this boundary, it can't escape the black hole's gravity. Time behaves strangely near black holes. As you get closer to a black hole, time appears to slow down, and at the event horizon, it seems to stop completely. But inside the black hole, time doesn't reverse. It's just that space and time swap roles. Instead of moving forward in time, you can only move inward toward the black hole's center. Inside a black hole, space and time behave in a way that's hard for us to imagine. There's a point at the center called a singularity, where our understanding of physics breaks down. We're not sure what happens there. It's a mystery that scientists are still trying to solve. Some think it might lead to another universe, but until we have a better theory of gravity, it's all just speculation. We all eventually have to come to grips with the end of our own time. our death. The prospect is sufficiently terrifying that many of the world's religions provide reassurance through claims that resemble some of the speculations about the time singularity of a black hole. They argue that death transports humans to a different realm, an afterlife, where time as we experience it does not exist. Many also explicitly forecast an end of times, where the existence of our worldly stage will disappear. In this sense, the possibility of a finite end of time in a black hole may not seem unfathomable. But pondering the beginning of time is even tougher. If time had a true start, it raises big questions about cause and effect. Scientists once thought the universe was static and eternal, but evidence of its expansion changed that in 1929. This expansion suggests that the universe began as an infinitesimal point about 13.8 billion years ago, a concept similar to a black hole singularity. The idea of the Big Bang faced criticism initially, but discoveries like the cosmic microwave background, CMB, confirmed it. The CMB is like a leftover glow from the Big Bang, supporting the idea that the universe was once much hotter and denser. This led to predictions about the abundance of elements like helium and lithium, which match observations. Such findings strengthen the case for the Big Bang theory. However, the concept of time around the Big Bang is mind-bending. While we experience time linearly, the early universe was incredibly hot and dense, causing reactions to happen at an astonishing rate. Imagine more reactions occurring in the first second of the universe's history than might happen in its entire future, even if it's eternal. Attempts to understand the moment of creation face major hurdles. The theory of inflation proposes that the universe experienced rapid expansion right after the Big Bang, erasing many clues about its early moments. Inflation might also make the universe eternal, with new pockets of space constantly emerging, each with its own Big Bang-like beginning. This suggests the possibility of a multiverse where different regions have different physical laws. Some theories propose that time itself emerged from quantum processes, or that the universe goes through cycles of expansion and contraction. However, these ideas are still speculative, and the true nature of time at the moment of creation remains a mystery, hidden like the secrets inside a black hole. Returning home after traveling is a comforting feeling, but while we can move freely in space, time only goes forward. The idea of traveling back in time, like in movies or books, raises tricky problems called paradoxes. For example, if I went back and changed the past, it might mean I wouldn't exist in the present. Some physicists think traveling in time might be impossible because of problems like this. One big problem is that a time machine would also have to be a space travel device. Earth moves through space, so if I went back in time just a short while, I could end up floating in empty space far from Earth. This makes time travel seem really tricky. Despite these challenges, some equations in physics suggest that traveling in time could be possible in certain situations, like through something called a stable wormhole, a kind of shortcut through space. However, creating stable wormholes might need special kinds of energy we can't make yet. So, while time travel is a fun idea in stories, making it real might be much harder than it seems. But who knows? Maybe in the future, we'll figure it out. Finally, is there actually an end of days for our universe? The Bible may favor such a future, but the data suggests otherwise. The observed expansion of the universe appears to be accelerating due to the presence of a non-zero energy permeating all of space. In this case, the rest of the universe will essentially disappear on a timescale of a few trillion years, and all that will be left will be our own galaxy, which by then will have collided with several other galaxies and will have become transformed to a roughly elliptical shape, no longer the lovely spiral shape it possesses now. We can consider ourselves lucky to live at a time when we can see so many other galaxies, as astronomers on planets a few trillion years from now will observe only one. Eventually, the stars in our galaxy will burn out, and the black hole at the center of our galaxy may grow to devour all the rest of the mass in our galaxy. But if Hawking is correct, the black hole will eventually radiate away and disappear much, much later, and all that will be left in the space we now occupy will be a cold, dark, apparently empty universe. You may have noticed several ifs in the last few paragraphs. This dismal future is the future as it might be in the spirit of Charles Dickens, because we don't know if the presently observed energy of nothingness, of space itself, is really a fundamental property or just a transitory one, like the energy that drove a presumed inflationary phase in the early history of our universe. If that energy disappears, then the future expansion of the universe could be dramatically different, depending both on the unknown geometry of the universe on a scale larger than we can currently measure and the unknown properties of space itself. For while the currently measured energy of empty space might one day disappear, who is to say there is not a much smaller residual energy of space that might remain? And who is to say whether this energy is positive or negative? If it is negative, the universe will ultimately collapse. When people ask if the universe is infinite or what's outside it, it's not easy to answer in a simple way. But let's try. Imagine the universe like the surface of a sphere. On a sphere, there's no inside or outside because it's all just the surface. Similarly, the universe might be like this, where there's no outside. If it's expanding, it's not expanding into anything, it's just getting bigger. For much of the 20th century, after Einstein developed his general relativity theory, the business of cosmology lay partially in trying to discover what the geometry of the universe was on its largest scale, namely, whether we live in a flat or open universe, either of which would in principle be infinitely big, or whether we live in a closed universe, in which case space is finite in size. And if you look far enough out into any direction, you will eventually see the back of your head. The reason for the intense interest in discovering the universe's geometry was that for a universe with gravitational dynamics governed by the energy of matter or radiation, geometry determines destiny. Namely, the ultimate future of the universe depends simply on whether the universe is open, closed, or flat, which is why determining which geometric pattern described our universe became the holy grail of cosmology. Now, the universe can have different shapes. It could be flat, like a piece of paper, or curved, like the surface of a ball. If it's flat, it goes on forever. If it's curved, it can still be infinite or finite, like the surface of a sphere. Scientists used to think the universe might be open or closed, which would affect its destiny. But then they discovered something called dark energy, which makes the universe expand faster. Now, no matter the shape of the universe, it will keep expanding forever unless something changes. Beginning around 1990, however, another problem began to emerge. Careful studies of the gravitational dynamics of galaxies and clusters suggested that accounting for the dark matter dominating these systems would only produce about 20 to 30% of the total density needed to result in a flat universe. Once again, observers were being driven to the conclusion that the universe in which we live might be open, not flat. Some scientists think the universe might be exactly flat, like a piece of paper. But even if it seems flat to us, it could still be finite, like a sheet that's been stretched really far. If we take a flat piece of paper and identify two of the edges, we form a cylinder. If we identify the other two edges, we form a donut. Geometrically, these look flat in the sense that straight lines remain straight, but clearly unlike a flat piece of paper, they have no edges. And unlike a flat piece of paper without edges, they are finite, not infinite. It is theoretically possible that our three dimensions of space contain non-trivial topology, namely that distant points viewed in different directions are actually the same physical point, and our universe, though apparently flat, is finite in spatial extent. Indeed, one analysis of data by Roger Penrose and colleagues suggested evidence for non-trivial topology in our universe. However, the analysis was subsequently disputed, and moreover, there is no compelling theoretical argument suggesting our universe would possess such features. As a result, this remains an unlikely theoretical possibility without current observational support. Nevertheless, as we open up new windows on the universe, we could be surprised. Understanding what's beyond our visible universe might seem impossible, but there's hope. If inflation theory is right, it suggests that even though we can't directly see beyond our cosmic horizon, we can indirectly learn about it. During inflation, space expanded rapidly, erasing most information about what came before. But some quantum processes during inflation leave traces we can detect today. like small density variations that eventually lead to galaxy formation. These variations show up in the cosmic microwave background, CMB, which is like a snapshot of the early universe. By studying the CMB, we can learn about the universe's history, although it's limited to about 380,000 years after the Big Bang. One way to learn more is by looking for gravitational waves from inflation. These waves are ripples in spacetime caused by massive events, like the collision of black holes. Detecting them is tough because gravity is weak, but it could provide evidence for inflation and help us understand quantum gravity. However, finding these waves is incredibly challenging, and while we haven't found them yet, it doesn't mean inflation didn't happen. It's like when scientists discovered atoms indirectly before they could see them with microscopes. If we can find evidence for gravitational waves from inflation, it could support the idea of a multiverse, a vast collection of universes, each with its own laws of physics. This idea might sound strange, but it could explain why our universe is the way it is. It's like if there are infinite universes, then anything that can happen will happen, including ones just like ours, but with small differences. This opens up a world of possibilities and challenges for physicists, but it also offers hope that new universes are continually being born, even as others fade away. There is a German quote often attributed to Goethe, but which is apparently actually from Schiller, which can be literally translated as, "The hardest thing of all to see is that which is in front of your eyes." Recent results in fundamental physics suggest that this may be literally as well as metaphorically true. Indeed, it is possible that whole new universes might exist just beyond the tip of your nose, while remaining potentially eternally undetectable. There's a quote often linked to Goethe, but it's actually from Schiller, saying it's hard to see what's right in front of us. Recent physics suggests there might be hidden dimensions beyond our usual ones. Think of it like the wardrobe in The Lion, the Witch, and the Wardrobe, leading to a whole new world. Physics struggles to explain why our space has 3 dimensions. Some think there might be more. Einstein suggested that gravity warps space. In formulating their theory, Kaluza, being a mathematician, never bothered with the obvious question that Klein, a physicist, clearly needed to address. If there is an extra 5th dimension, why don't we see it? His answer was clever. If the extra dimension were curled up into a tiny circle and were very small, none of the experiments we performed here on Earth would be able to peer inside this very small circle. There is a simple analogy that has often been used to describe this. Imagine a soda straw, with the length along the straw being space as we observe it, and the length around the circle enveloping the straw's circumference being the extra dimension. If that circumference gets smaller and smaller, eventually the straw will just look like a line to us, and the extra dimension will have become invisible. This cute picture might have been consigned to the dustbin of history were it not for the development of what became known as string theory 60 years later. Physicists trying to develop a quantum theory of gravity, a theory which might consistently unify general relativity with quantum mechanics, discovered that a theory in which the fundamental space-time objects were not points in space and time, but rather string-like objects, could be turned into a quantum theory, and the equations of general relativity naturally arise as the classical limit of this quantum theory. String theory suggested that particles aren't points but tiny strings, requiring more dimensions, initially 26. Later, it was reduced to 10 or 11. These dimensions could be hidden in tiny balls smaller than atoms. Some theorize that gravity is weaker because it extends into extra dimensions. This could explain why we can't see them. But experiments haven't proven this yet. Another idea suggests that gravity behaves strangely in extra dimensions, which could be infinite in size. But this theory is controversial. The holographic principle suggests that a lower dimensional surface can contain all the information of a higher dimensional space. This could mean our universe is like a hologram, with fewer dimensions than we perceive. Whether or not the ADAS-CFT conjecture actually relates to the nature of our spacetime, As a tool, it has been incredibly useful in physics because it allows us to relate the physics of some strongly interacting theories, which are themselves too complicated to perform accessible calculations with, to theories of pure gravity, which may be much easier to work with. Aside from these technical issues, of which there are many, there is a deeper question here. If an n-one-dimensional surface can encode all the information associated with the n-dimensional world it encloses, does dimensionality really mean anything significant? In this case, is the actual world n-dimensional or n-one-dimensional? Of course, we don't know. But for some, the enticing possibility remains that the four-dimensional world we call our universe is actually a hologram. What is the world made of? This question echoed through the ages, driving humanity's quest for understanding the fundamental nature of reality. In their pursuit of answers, scientists delved deep into the atomic picture of matter. They discovered that everything around them, from the air they breathed to the ground beneath their feet, was composed of tiny, indivisible particles called atoms. These atoms, they found, were like miniature solar systems, with a nucleus at the center surrounded by orbiting electrons. But the story didn't end there. As scientists peered even deeper into the fabric of reality, they uncovered a world even more intricate and mysterious, the world of subatomic particles. These particles, they realized, were the building blocks of atoms, the fundamental constituents of matter itself. The journey into the subatomic realm led scientists to develop the standard model of particle physics, a comprehensive framework that described the fundamental particles and the forces that govern their interactions. According to this model, there are two categories of particles: fermions and bosons. Fermions are the building blocks of matter. They include quarks, which combine to form protons and neutrons, the building blocks of atomic nuclei, as well as electrons, which orbit the nucleus of atoms. There are 6 types, or flavors, of quarks, each with its own unique properties, and 6 types of leptons, which include the electron and its 2 heavier cousins, the muon and the tau. Bosons, on the other hand, are the carriers of the fundamental forces of nature. They include the photon, which mediates the electromagnetic force, the W and Z bosons, which mediate the weak nuclear force responsible for radioactive decay, and the gluon, which mediates the strong nuclear force that binds quarks together inside protons and neutrons. Together, these particles and forces form the intricate tapestry of the universe, governing everything from the behavior of atoms to the interactions of galaxies. Yet, despite our deep understanding of the Standard Model, mysteries still remain. Scientists continue to search for answers to questions such as the nature of dark matter, which makes up the majority of the mass of the universe, but remains invisible to our telescopes, and the existence of the Higgs boson, which gives other particles their mass. The quest to understand the fundamental nature of reality is far from over. But with each new discovery, humanity moves one step closer to unraveling the mysteries of the universe. Humphrey Bogart, in The Maltese Falcon, famously referred to a valuable object as the stuff that dreams are made of, a line inspired by Shakespeare. Similarly, throughout history, scientists have pondered the basic building blocks of matter, from ancient Greek philosophers like Democritus proposing atoms to modern physicists discovering subatomic particles like electrons and protons. Democritus first suggested the idea of atoms, though he didn't know much about them. Later, scientists like Ernest Rutherford found that atoms weren't indivisible, but had a nucleus at their center, surrounded by electrons. Rutherford's experiments showed that atoms were mostly empty space, with a dense nucleus. The mystery of atomic structure deepened until James Chadwick discovered the neutron in 1932, completing the picture of atomic nuclei containing both protons and neutrons. However, neutrons turned out to be radioactive when not bound in nuclei. Despite being more abundant than protons, neutrons decay into protons after about 10 minutes when they're not part of an atomic nucleus. This decay process puzzled scientists because it violated certain laws of classical physics. Wolfgang Pauli proposed the existence of an invisible particle, the neutrino, to carry away the excess energy and momentum from neutron decay. Enrico Fermi embraced Pauli's idea, and eventually, in 1956, Fred Rhines and Clyde Cowan successfully detected neutrinos, confirming their existence. This discovery, along with others, contributed to the development of the standard model of particle physics. Particles like electrons, protons, and neutrons act as if they're spinning, even though they're not really spinning like a toy top. This spin is a kind of angular momentum they carry with them. In the quantum world, they can seem to be spinning around different axes all at once until we actually measure their spin along a specific axis. These particles have what's called spin half, which means they can have two different spin states along any axis, either plus and half or minus and half units of angular momentum, or a mix of both. Sheldon Glashow proposed a theory where W and Z particles exchange like photons but are heavy, explaining the weak force's short range and weakness. But this begged the question of why W and Z particles were heavy while photons were massless. Steven Weinberg and Abdus Salam proposed a mechanism involving a field called the Higgs field, which interacts with particles and gives them mass. This idea, while fantastical, preserved the mathematical symmetry of the theory. The existence of W and Z particles was confirmed in 1983 at CERN, using detectors to identify unique decay signals. This discovery validated the theory of the weak force and the role of neutrinos, which only interact through the weak force. As important as this experimental discovery was, one central and seemingly the most contrived piece remained missing from the elegant electroweak unification theory. The piece that gave the WZ and all other elementary particles mass, the Higgs field. For nearly 3 decades after the discovery of the W and Z particles, physicists hunted for the Higgs boson, a crucial piece of the puzzle in understanding how particles get their mass. They searched with increasingly powerful machines, culminating in the Large Hadron Collider at CERN, which eventually found the Higgs in 2012. But the Higgs discovery brought more questions than answers. Its properties seem arbitrary, and its mass poses a problem in our understanding of quantum physics. The Higgs interacts with virtual particles, tiny fluctuations in the quantum field, which should make its mass infinitely large. Yet it's not. This problem, called the hierarchy problem, led theorists to propose supersymmetry, a theory connecting particles with different spins. Supersymmetry suggests each known particle has a partner with the opposite spin. These partners could cancel out the quantum effects on the Higgs mass, solving the hierarchy problem. While supersymmetry hasn't been directly observed yet, its existence could explain why we haven't seen the superpartners in our experiments. But as time goes on without evidence, the theory's credibility weakens. Its implications extend beyond particle physics, potentially impacting our understanding of gravity and even string theory. Electrons, protons, and neutrons form atoms, but only electrons are thought to be truly fundamental. Protons and neutrons are made up of smaller particles called quarks. Quarks were first proposed as mathematical building blocks of protons and neutrons to solve puzzles in particle physics. Initially, they were seen as theoretical entities, but their existence was confirmed in 1969 through experiments involving electrons and neutrinos. These experiments revealed that protons indeed consist of smaller particles with fractional charges, just as predicted by the quark model. However, there were puzzling aspects. The quark-like particles inside protons seemed to move freely, and no experiment had ever knocked out a bare quark. The solution came unexpectedly. Physicists theorized that quarks interact with each other through a strong force, analogous to electromagnetic interactions, but with 3 different color charges. In 1972, it was discovered that this strong force behaves uniquely. It weakens as quarks get closer, a property called asymptotic freedom. This explained why quarks inside protons appeared almost non-interacting in experiments. Asymptotic freedom also hinted at another phenomenon called confinement, where quarks are forever bound together by the strong force. While this theory remains unproven, it's a crucial aspect of our understanding of particle physics. With the development of quantum chromodynamics, which describes the strong force, and the successful unification of the weak and electromagnetic forces, physicists gained a solid understanding of 3 out of the 4 fundamental forces in nature. This formed the basis of the standard model of particle physics by 1972. In 1929, the British theoretical physicist Paul Dirac figured out a way to unify quantum mechanics and special relativity, in turn producing a quantum theory of electromagnetism called quantum electrodynamics. It was a remarkable achievement that placed Dirac in the ranks of the greatest theoretical physicists of the 20th century. It also made a prediction that he found embarrassing. The equation he derived, now called the Dirac equation, had an unexpected implication. In modeling the relativistic quantum states of electrons, the equations required a new set of states, of seemingly negative energy. These states could alternatively be considered positive energy states, but only by assuming the existence of particles with an electric charge equal and opposite to that of the electron, but with otherwise equal mass and other properties. Dirac was flummoxed. He proposed that perhaps seemingly empty space was full of a sea of negative energy electrons, now called the Dirac sea, and that they were undetectable. With enough energy, one could kick an electron out of this sea and produce a real observable electron. That would leave one less electron in the sea, which would therefore appear as if it left an equal and opposite positive hole, the absence of a negative electron in the sea. He argued that perhaps the interactions of that hole with other electrons in the sea would cause it to behave like a heavy positive particle, which he identified with the proton. But it was quickly shown by Pauli and others that this argument didn't fly. Dirac's confusion didn't last long. Within a year of the development of his theory, the American physicist Carl Anderson, examining the tracks of cosmic ray particles in detectors, discovered among the cosmic rays a track corresponding to a particle that resembled an electron in every way except that it was positively charged. It was quickly recognized that this particle, dubbed a positron, was precisely the particle predicted by Dirac's theory. Dirac himself later said that his equation was smarter than he was. It is now understood that as a consequence of the combination of quantum mechanics and special relativity, all elementary particles like electrons and quarks must have what are now called antiparticles, partners with equal mass and opposite charge. Some neutral particles, like photons, the carriers of electromagnetic interactions, can be their own antiparticles. Just as positrons must exist, so must antiquarks, which can make up antiprotons, and so on. All such antiparticles have now been detected, and indeed, it has become routine to produce them in elementary particle accelerators. In fact, physicists can create beams of antiparticles and collide them with particles in order to further explore the properties of matter and radiation. Antiparticles seem like the stuff of science fiction, but they are not. When a particle and antiparticle collide, they can convert their mass energy into pure radiation. But other than that, antiparticles behave essentially identically to their particle partners. They fall down in a gravitational field just like particles. Antihydrogen, comprised of bound states of a positron and an antiproton, has essentially exactly the same atomic spectrum as hydrogen. We only call antimatter by that name because we happen to be surrounded by matter rather than antimatter. Why does our universe consist mostly of matter and not antimatter? This is known as the Baryon asymmetry problem. According to our understanding of physics, the early universe should have had equal amounts of matter and antimatter. However, if that were the case, they would have annihilated each other, leaving only radiation. Yet, here we are, made of matter. This suggests that there was a slight excess of matter over antimatter in the early universe. The challenge is to explain how this imbalance arose. Physicists like Sakharov outline 3 conditions necessary to create this asymmetry: interactions that can create or destroy the net number of baryons, departure from thermal equilibrium in the early universe, and violation of symmetry between particles and antiparticles. CP violation, discovered in the weak interactions of particles, is one aspect of this asymmetry. However, it's too small to account for the observed matter-antimatter difference. Other mechanisms, such as phase transitions and exotic processes, may have played a role. Furthermore, the standard model of particle physics suggests that all known forces could be unified at high energies. This grand unification could have implications for understanding the fundamental nature of matter and the universe's asymmetry. The concept of grand unification in particle physics was once very exciting, but it faced challenges upon closer examination. Proton decay experiments, designed to detect signs of grand unification, haven't yielded any results so far. However, this doesn't rule out the idea entirely, as different models suggest different outcomes. Another issue is that the strengths of the fundamental forces don't converge at a single high-energy level as expected. However, the proposal of supersymmetry, which introduces new particles, helped reconcile this problem by shifting the convergence point to a higher scale. Despite these potential solutions, experiments at the Large Hadron Collider haven't yet found evidence for supersymmetric particles. This leaves physicists uncertain about the future of grand unification and supersymmetry. Grand unification also connects to the long-term fate of the universe. If protons decay, which might happen over an incredibly long time span, then eventually all matter will disappear. This raises questions about what might exist in the distant future universe, but we currently lack answers. Neutrinos, which are tiny particles with almost no mass and hardly any interaction with matter, have been involved in many breakthroughs in understanding the fundamental building blocks of the universe. But oddly, they've been absent from recent discussions about unsolved mysteries in physics. Now, it's their turn to step into the spotlight. In the past, our knowledge of physics beyond the standard model, like the imbalance of matter in the universe and grand unification, has mostly been indirect. But one direct clue came from studying neutrinos. According to the standard model, neutrinos were thought to be massless and only have one type of spin. But experiments in the 1960s and 70s revealed something unexpected. The solar neutrino problem was a puzzle where observations of the sun didn't match predictions. Physicists suspected neutrinos might be changing types as they traveled, which could explain the discrepancy. This idea led to the search for neutrino oscillations, where one type of neutrino can morph into another. The Sudbury Neutrino Observatory confirmed this in 2001, showing that neutrinos do indeed have mass and can change types. This discovery shook up our understanding of physics because it couldn't be explained by the standard model alone. It suggests the existence of right-handed neutrinos, which could have profound implications, like explaining why there's more matter than antimatter in the universe. Neutrinos could also hold the key to unlocking other mysteries, like why their masses are so small, and whether they can cause a type of violation in the laws of physics that we haven't seen before. Massive experiments are underway to explore these possibilities. So, will neutrinos help us solve the puzzles of the universe? We're not sure yet, but it's an exciting journey to watch unfold. Among all the mysterious features of matter at fundamental scales in nature, perhaps none is stranger than that which determines the rules that govern the behavior of matter. Quantum mechanics is a bizarre but crucial aspect of understanding the universe. It's like the rulebook for the tiniest particles and their behaviors. Even though it seems crazy, we can't ignore it because it's the foundation of modern technology, from computers to smartphones to cars. Discussing all the subtleties of quantum mechanics would require an entire book, but it is possible to more succinctly outline the various key features that underlie our quantum universe. Multiple states at once. Unlike classical physics, where things follow predictable paths in quantum mechanics, particles can exist in many states simultaneously. This idea, championed by physicist Richard Feynman, means that until we measure a particle, it's like it's taking every possible path at once. Wave function. In quantum mechanics, we use something called the wave function to predict the likelihood of finding a particle in different states. This doesn't mean it's random. There's an equation that describes how the wave function changes over time, determining the probabilities of different outcomes. Measurement order matters. The order in which we measure properties of a particle can affect the results we get. This leads to things like the Heisenberg uncertainty principle, where we can't know both the position and momentum of a particle with complete accuracy. Entanglement. Even when particles are separated, they can still be connected in a way that measuring one instantly affects the other. This is called entanglement, and it's what Einstein famously called spooky action at a distance. Quantum fluctuations. When we combine quantum mechanics with Einstein's theory of relativity, things get even weirder. Even empty space isn't truly empty, with particles and antiparticles popping in and out of existence on incredibly short timescales. These points highlight the strangeness of quantum theory, where the familiar rules of classical physics break down. Some physicists have tried to come up with alternative explanations, but so far, quantum mechanics has stood up to every test. How did an inanimate universe become animate? That question has been the cause of wars and the inspiration for artists, painters, writers, and of course scientists. More than any other physical observable, life appears akin to a miracle. For many people, perhaps most people alive in the world today, it still is. Yet, at the heart of science is the presumption that natural effects have natural causes. If we accept that life is subject to physical laws, we are obliged to then move from the sacred to the profane, or at least to the natural. The question of how life emerged from non-life has fascinated people for centuries, inspiring artists, scientists, and philosophers alike. Science tells us that everything in the universe follows natural laws, including life, which means we need to look for natural explanations. While biology usually tackles questions about life, it's ultimately governed by the laws of physics and chemistry. Some great physicists like Erwin Schrödinger even explored the nature of life. Defining life isn't easy. We might say living things reproduce, have metabolism, and respond to stimuli. But then, is fire alive? Probably not, because it lacks homeostasis, a crucial aspect of life. Viruses pose another challenge. They can't reproduce on their own, but hijack other cells to do so. Despite this, viruses seem alive in some ways because they have strategies for survival and reproduction. Viruses might have even played a role in the evolution of life, possibly merging with other organisms to enhance their capabilities. One famous example is mitochondria, which were likely once independent organisms before being assimilated into other cells. But how did it begin? Is life on Earth unique? Is life elsewhere in the universe different from what we know? These are the mysteries that continue to drive scientific exploration. When we think about how life began, we realize that even the simplest life forms are incredibly complex. Some people argue that this complexity suggests a supernatural explanation is needed, but science suggests otherwise. Chemical reactions, like life itself, aren't completely random. They're influenced by physical concepts like entropy and enthalpy. Even seemingly random processes like diffusion show directionality. Despite the complexity of life, it's sustainable because it follows the laws of thermodynamics, which allow local order to increase at the expense of the environment. Life extracts energy from its surroundings, contributing to this order. Scientists have made progress in understanding the origin of life by exploring exotic environments where complex chemistry can occur naturally. Surprising discoveries, like RNA's ability to both store genetic information and catalyze reactions, suggest pathways for life to emerge from non-life. The origin of life is still a big mystery, but advancements in science make it seem more and more possible to find answers. Research into prebiotic chemistry, the presence of organic molecules in space, and the role of RNA provide promising avenues for exploration. Whether or not we discover signs of life elsewhere in our solar system or beyond, and I am personally quite confident we will. As Carl Sagan's protagonist in Contact once said, if we are alone in the universe, it is an awful waste of space. What will really be most fascinating will be what kind of life we discover. At least 3 possibilities exist. First, we might find life that's similar to what we have on Earth, using the same basic building blocks. This seems likely because the conditions for life here could be common elsewhere. Another idea, called panspermia, suggests life may have started elsewhere and traveled to Earth. But this doesn't really solve the mystery of life's origin. It just pushes it back a step. Then there's the chance we find life with completely different rules, maybe based on different chemistry or energy sources. This could happen on planets with different conditions. Finally, there's the most exciting possibility: life that's totally alien, unlike anything we know. While we focus on places similar to Earth to search for life, we shouldn't assume it's the only way life can exist. If we don't find life where we expect, it doesn't mean it's not out there somewhere. The fact that we have no idea at all about the possibilities for life is exciting, but it should also temper our confidence in making estimates about the probabilities for life in the universe, particularly intelligent life, and also about the future of life in the universe. In 1961, the astronomer Frank Drake wrote down what is essentially a mnemonic to guide thinking in order to estimate the number of active, intelligent, and communicative civilizations in the Milky Way. It has since become known as the Drake equation, although it is not really an equation, but rather a back-of-the-envelope expression of the known unknowns. An estimate for the number of communicative civilizations is given as the product of a series of probabilities, almost none of which we have any empirical handle on. One of those probabilities was the fraction of stars that have planets around them, which we now know is approximate unity. The rest, the fraction of planets that can potentially develop life, the fraction that then do develop life, the fraction that develop intelligent life, the fraction of intelligent civilizations that develop communicative technologies, and the fraction that then attempt to communicate, were essentially just wild guesses at the time, and to a large extent still are. We may never have an empirical handle on all of these probabilities, but we can pin some down. JWST, for example, may reveal the signatures for living systems on some planets, which would, for the first time, tell us that one of the key probabilities in Drake's estimate isn't near zero. The rest will depend upon learning more about the origin of life than we currently know. It is possible that chemists will determine the likely prebiotic pathway to an RNA world, or something like it, here on Earth. But, as I indicated earlier, I suspect that the discovery of other genes of life elsewhere may be required in order to confirm such a pathway, or to get a handle on the full variety of possibilities. If there are many different routes to life, these will undoubtedly include paths we would not otherwise suspect, because of our limited experience here on Earth. If organic life forms with fundamentally different biologies are discovered in our solar system, that will tremendously increase the odds that life is flourishing throughout our galaxy. And if new extraterrestrial extremophiles are discovered, such as life forms on Titan, then the possible locales for life to exist in the galaxy will be further multiplied. Our emerging knowledge about life on Earth suggests that living systems here have colonized essentially every possible niche on the planet. Perhaps the same is true writ large for the galaxy. Astrobiology, the study of life beyond Earth, is still young. Many claims in the media about aliens should be taken with a grain of salt, since there's more guesswork than solid evidence. But there are reasons to be hopeful. There are loads of stars and planets out there, and Earth formed pretty early in cosmic history. Plus, the basic stuff for life, like water and organic materials, is all over space. So it seems unlikely we're the only life-friendly spot in our galaxy, let alone the universe. But when it comes to intelligent life like us, it's a different story. It took a long time for humans to evolve, and there's no guarantee it happens everywhere. Our own journey to intelligence had some lucky breaks, like dodging big space disasters and surviving earthly catastrophes. Our understanding of different kinds of intelligence is still pretty limited, which makes it hard to answer big questions about life in the universe. And even if civilizations get smart enough to invent cool tech, they might not stick around long enough to chat with us. So, whether we'll ever meet other spacefaring beings is still a big mystery. The future of life on Earth and in the universe raises many questions. Can life here survive the changes our planet and solar system will undergo? And does life's fate connect to the destiny of the universe itself? Despite any human impact on Earth's climate, the long-term outlook is influenced by the Sun and galaxy. Unfortunately, the Sun's brightness is increasing over time, which could eventually lead to Earth becoming uninhabitable. In billions of years, the Sun will expand, possibly engulfing Earth. However, if intelligent beings survive until then, they might find ways to save the planet, like moving it to a safer orbit. Some suggest moving life to Mars as a backup plan. But sending humans far into space is tricky due to biological limitations and high costs. Instead, sending instructions for creating humans might be more practical. Discussions about the future also touch on bigger cosmic questions. Can life last forever? Some suggest that in an expanding universe, life could hibernate during cold periods and awaken to new insights, possibly lasting indefinitely. However, new challenges arise when considering dark energy's effects on the universe's future. It seems that life's persistence might be limited in the long run. Yet, there are intriguing ideas, like a hypothetical black cloud life form, that challenge our understanding of life's possibilities. Ultimately, our imaginations about life in the universe should be open-ended. While civilizations may rise and fall, the universe's vastness suggests that life in some form, may endure. Some people wonder if life was created by a grand designer. While there's no evidence for this, some still find the idea appealing. Darwin and Wallace showed that life's diversity and fitness for its environment can be explained by natural selection, not divine design. Similarly, in cosmology, some argue that certain fundamental constants of the universe seem finely tuned for life to exist. But this overlooks that life adapts to fit its environment, not the other way around. For example, the discovery of dark energy, with a value much smaller than expected, raised questions. Some suggest this fine-tuning points to a divine planner. However, if dark energy had been precisely zero, the universe might actually be more suitable for life. The truth is, we don't know all the possibilities for life or how it might adapt to different universes. So, assuming the universe was made just for us is presumptuous. Rather, it's a reminder of our limited understanding and the need to stay curious. Considering hypotheticals like Hoyle's black cloud should keep us humble and open-minded about life's mysteries.